Thank you. I'm Xuan from Georgia Tech, and I have been working with my student, supported by the CyberGIS grant. And last year, Fei was in the first all-hands meeting in Oak Ridge, and now Xuan is here with me today. I will give an overview on the infrastructure we have been working on, and a brief overview about the software modules we developed in this past 1.5 years. So the infrastructure we used actually two supercomputers. One is Cregan. It's a heterogeneous or hybrid computer system. It's a 5-year cooperative agreement awarded by National Science Foundation for $12 million, and developed by Georgia Tech, University of Tennessee at Knoxville, and Oak Ridge National Lab. And Cregan has 120 nodes, and each node has 2 CPUs and 3 GPUs. And it just integrated into XD in last month. And I think the Blue Waters will be the full-scale hybrid computer system like Cregan. So that's the first one. The second one is Kraken. Kraken does not have GPUs, but it was the 8th fastest computer in the world in 2010, and was the first academic supercomputer enter the petascale capability. So Kraken has a total number of more than 112,000 cores, and we can use the supercomputing resource to do spatial computation. So we start from parallelizing the IDW Interpolation algorithms. So initially we just write a serial program, and then we parallelize that on a single GPU, and eventually we move that to scale up onto Cregan. And here is the result. And we can see for the interpolation, the outer grid has more than 1 million cells. And the size of the input data points is on the first column. You can see from 2,000 points to about 10,000 points. And eventually, when we scale this up onto Cregan, when we use 3 GPUs, we can achieve a speed of more than 1,000 times faster than the same program running on a desktop machine. So, and from this table, we can find the solution is scalable, but only when we use 3 GPUs, we get the best performance. But we can see we can scale this up onto 6 GPUs, 9 GPUs, or more than this, but we don't get better performance in this case. So this means the scale of this problem is not that big. So 1 million cells is not a big deal on the supercomputers. So maybe we can try 1 billion cells in the future in this case. And for IDW interpolation, we use 12 nearest neighbors. But when we do the Cregan interpolation, we can only use 10 nearest neighbors, because we want to compare the performance on the single GPU on a desktop machine, because that's a very old GPU. So that GPU has a limited memory. If we use more than 10 nearest neighbors to do the interpolation, it's out of memory. So in this case, we can see we can still get a significant speed up in this case. But on Kinland, we can use 12 nearest neighbors to do Cregan interpolation without any problem. So from this works, we can see the larger the data set, the better performance we can achieve. And a second work, the third work we did is about the parallelization for cellular automata. And it's a foundation for many geospatial modeling and simulation, such as the sleuth model for urban growth simulation. And we start to use a very generic CA model. It's called the game of life. And the simulation is based on some rules. So you can see whether this cell is alive or dead or generate new status. It depends upon its neighbors. So in this case, if we initialize a grid after many iterations, you can see the result. So eventually, if we run the simulation for a long time, we will get an empty grid at the end. So CA, parallelizing CA is something different from what we did on interpolation calculation, because interpolation is an invariantly parallel issue, but for CA, we can see there are a lot of communications in this case, because when we calculate the status of one cell, its status is dependent upon its neighbors. So when we cut this into pieces and distribute the data onto different computing nodes, we need to share the information about the boundary columns or rows. So in this case, we run the CA over a grid size for 10,000 by 10,000. So I was told by my collaborator, and in urban simulation, they may not go beyond a 4,000 by 4,000 grid. So we just tried 10,000 by 10,000. And the serial program runs for 100 minutes, and eventually when we use 20 GPUs on Kinland, we reduce the time to 20 seconds in this case. And in the summer, we just implemented a simple sleuth model on a single GPU. So our next step will move this onto Kraken and Kinland using multiple GPUs. And the fourth one is parallelization for the ISO data algorithm. It's a classic algorithm for unsupervised image classification. So in this case, we have a single GPU version, but eventually we found we need to handle a lot of memory issues. So we just try to implement the ISO data on Kraken first. And the data is a high-resolution image. It's about 0.5 meters resolution. And one tile of the image has 18 gigabytes. And we eventually can process 216 gigabyte image in a single process. And we can finish the classification process within 10 seconds. And eventually we did some more classification tests, and you can see we can accomplish the process within 1 minute when classified this bunch of big images into 10 classes, 15 classes, and 20 classes. And we can see the performance in comparison to others imagined. And the last one is a spatial temporal analysis on crime events. And it's easy to go beyond petascale and exascale or iota scale. So in this case, we just using more than 20,000 cores on Kraken, and we just used our allocation time. So, but we get a significant speed up in this case, because traditionally researchers do something on desktop can never handle this problem, because and actually the total events is only about 30,000, so that's not a big deal. But when we do the comparison, it's easy to go beyond the petascale, exascale problem. So thank you.